Hello everyone. Today we're going to begin looking at representing functions as series, which is really one of the biggest powers of calculus, and it's exciting to finally be getting here. So before we do that, we're going to need to jump into a quick review of our geometric series that we did earlier. So what was a geometric series? You start out with a first term, and then each subsequent term is a multiple of some factor called r. And so what we'll see is a common example is like 1, 1/2, 1/4, 1/8, dot, 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 as r keeps multiplying everything by 1/2. So that's a very common example. We'll come back to that. So we need to figure out how do we find a sum of a geometric series. Well, the common trick here is to multiply by r. And so you end up getting two sets of series. And what's nice is you'll notice that these happen to cancel all the way through the series. So if we take list 1 minus list 2, that's right here on line 3, the only thing left is the first term and then the last term, because all these middle terms cancel out. So that's quite a nice trick. Factor out the s, divide by 1 minus r, and you get the formula for the sum of a finite geometric series. So you're going to want to remember this formula. It's quite useful. And we'll do some practice problems here with it. So why do we know that this formula works? Well, let's just do a test case just to make sure. So this is a series that starts with 1. Notice I is becoming at 0. So when I is 0, the first term is 1, and then 1/2, 1/4, 1/8, which is here represented in expanded form. And you could always notice, like, sometimes it doesn't start at 0. Sometimes your index here starts at 1. Well, that's just a indices shift here of -1. So when I equals 1, 1/2 to the 0 power is still 1. So it's starting at 1 either way, and then multiplying by 1/2 through. So if we were to just do this, with our barbaric mathematics skills, we would just add it up as decimals and come up with this nice smooth answer. But now that we have this formula that we derived on the previous page, let's just test that to make sure that our formula is getting the answer we're expecting. So A1 is of course your first term. R is the common ratio. So that's 1/2, 1/2, 1/2. And then R is 1/2. And the N is the number of terms. So 4 terms. And we've listed those out here. And then we just plug and chug into our formula. And boom, same answer. So it seems like our formula is okay. Of course, this is just a single case, but it is indeed true. Okay. So now we're going to be interested in what happens with the same situation where we're adding this 1/2 factor each time. And we want to say if we do this indefinitely, or we go for infinitely many terms, and what's going to be the outcome of the sum. And here you'll see that we're starting at 0. And we're going until n, but this term is actually tending towards infinity. And so you'll know when I is 0, we get the 1. When I is 1, we get 1/2. When I is 2, 1/4. When I is 3, 1/8, dot, 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 indefinitely. Now we can actually do this visually with a nice square. All right, so we assume this is a square of length 1. Well, then 1 by 1 is 1. That's our first term. And then we're going to take 1/2 of that. And then we're going to take 1/2 of that 1/2, 1/2 of that 1/2, 1/2 of that 1/2. So we get squares that have 1/2 area, 1/4 area, 1/8 area, 1/16, 1/32, 1/64, dot, dot, dot. We repeat this pattern indefinitely. And you'll notice, if I continue doing this forever, we will be converging to this total area of a brand new square. So it's likely that this 1/2, 1/4, 1/8, dot, dot, dot will converge to another complete square. So a whole square plus another square will make 2 whole squares. Geometrically very, very precise, very believable. But now let's say we want to apply our formula to that. So we have a geometric sum that's finite. And we're using first term 1, r 1/2, and approaching infinity. So when we're doing this mathematically, it's important that you don't just plug in infinity here. That wouldn't make any sense. So what you're technically doing, you're wanting to do a finite sum that has n terms inside of it. And those n terms are approaching infinity. So when we do the limit as n approaches infinity now, well, now when we plug in, instead of putting an infinity here, we now have a limit problem, which is much more mathematically precise. And what happens if you take 1/2 to a power that is approaching infinity? Well, 1/2, 1/4, 1/8, 1/16, 1/32, dot, dot, dot. These numbers are getting smaller, smaller, and smaller. So you could say that eventually this limit will approach 0. And this whole term will actually disappear, making the calculation quite easy. 1/1/2 from this step here, 1/1/2 makes 2. So again, our geometric sum formula for finite terms proves to get an answer that we're expecting. So we're pretty happy with that so far, I hope. So let's move on. Quick recap, this is your finite sum, remember that. Now, we just did an example where maybe we don't want to look at finite sums, we want to look at infinite sums. So we apply the same logic. Let's take the finite sum as the number of terms approaches infinity. Well, that means that this sum formula here that we derived, as this n approaches infinity, well, what is the conditions that this will happen to be 0? In our previous example, r was 1/2. And because r is 1/2, 1/2 to a power growing larger and larger reduces down to 0. And there's many types of powers that will do that, 1/3, 1/4, 1/5. Anything, essentially, what the kick here is, anything that is smaller than 1 or bigger than -1 will make this limit approach 0. And so we're going to put that condition right here. As long as the ratio, the common ratio, is between -1 and 1, the nth power as n approaches infinity will converge to 0. Therefore, this cancels and leaves a nice pretty answer. So we have this formula is the sum for an infinite geometric series only on the condition, so capital big IF here, that the absolute value of r is less than 1. And for the following cases, I will make sure that r is less than 1, but it's not guaranteed as we move forward, which is a big part of the next chapter. So for now, here's some practice problems. Some pretty cool uses for the geometric series. And we all know repeating decimal patterns. You can derive some pretty cool general formulas for this, like problem E and problem C. They're quite exciting for number enthusiasts. And then, of course, find the following sums. This is a geometric sum. You're looking for A1 and R. And this is also geometric, looking for A1. Make sure you take into account your starting indice. And here, this is also geometric. You're going to want to factor out the common ratio using your property of exponents and turn it into something that appears geometric. And this is your infinite series with the dot, dot, dot. And then, of course, this very nice geometric problem as well. So go ahead and pause the video, try these out. When you unpause, the next slides will be these solutions. And here I'm going to walk you through some of the solutions. Hopefully you paused the video and you went back and you tried them by yourself first. So quickly, 7, 8, 7, 8, 7, 8. That's a 0.78 plus a 0.78 shifted by 2 terms plus a 0.78 shifted by 4 terms. And when you get this sort of pattern, you'll notice that they all have a 0.78. The only thing changing is that this 1/100 is scaling. So there's no 1/100. Here there's 1/100. Here there's 2 1/100s, or squared, and then dot, dot, dot. So this is the geometric form where we take the first term. Notice my k is 0 and k is 0. So this is my first term. Plop it in. And 1 minus r, and that's my r, and we're left with 78/99 with some easy arithmetic. And then this one's a little interesting as well, this 23, 45, 45, 45. I think it's misnumbered from the previous slide, but that's okay. So you'll notice first that this repeating pattern of 4, 5, 4, 5 actually doesn't begin until the 1000th place. So we're going to start with a +2, 3, as the hundredths place. And then after that, we're going to start having this repeating pattern. And that repeating pattern follows the same exact template. So instead of starting at a 0.78, we're actually going to start at a 0.45 over 100. This is that shift of 2 decimal places to the right. And then, of course, jumping over by 100ths. So you get your starting decimal of 0.23, and then your some quick algebra here, your starting term, your 1 minus r, and that will reduce to this common state, which is going to be helpful for our solution in part E. Now, you'll see here that 23 was the repeat length, or the delay length, so it delayed 2 decimal places. And then you ended up having a repeat length of 2 digits, which is 454545. So that repeat length is going to cause 2 9s here, because this repeat length is 2 digits long, 4545. That's 2 9s right here on the 23. And because it's a repeat length of 2 units, then that's why there's 2 9s in the denominator. These 2 zeros are there because the 23 offset the repeating pattern by 2 decimal digits. So this is a very nice formula for replicating repeating decimals as a fraction. And you'll notice that is the exact solution that we end up getting here. So if I'm looking at this answer on example for part E, if I see a delayed length of 2 digits, well then I know that there's going to be 2 zeros in the denominator. And I see a repeat length of 1 on the 3's. So the repeat length of 1 is going to cause 1 9 here and 1 9 here. So very nice formula. Read through this proof or this solutions guide and let me know if there's any questions. And then here we got the solution to the geometric sums. Again, this is a finite sum, so we need to remember this formula here. The 1 minus r to the number of terms, 1 minus r. And you feel free to do a calculator here. This part's not important, this part is. And then this one's infinite actually, so it's the exact same term, but now it's infinite. And you'll notice this is actually quite a bit easier now, because you don't have to worry about 1 over 4 to the infinite power is 0. So we don't have to worry about that anymore, and the calculation becomes quite easy. For the negatives, don't forget that negative goes inside. Cleaning up the problem quite nicely. Again, calculator accessible. And for this property of exponents, pull that 2 out. And then this is 2 over 3 to the k power. And now it's geometric. Just make sure you know if your indice is at 0 or 1. So plug in that 0. That's going to cancel this for your first term to be 2. And then your r is 2/3. And for part 3, we did all the square sums, and we start out just to make it easy. We know the area has 4 square meters, so that is a 1 by 1 by 1 by 1. So 2 by 2 is the first square, that's 4. And if that's 1, 1, then this is root 2. So root 2 by root 2 makes it an area of 2. And now if this whole thing is root 2, then that means this part is root 2 over 2. And if that's root 2 over 2 and that's root 2 over 2, well then that's 1. It's your standard 45-45 ratio. So now this is a 1 by 1 square. So if we have this sort of pattern here where we have 4 by 2 by 1, it's clear that each square is getting an area cut in half. So speculate as to what 4 and 5 would be. Well, half, 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 half. So 4, 2, 1, 1/2, 1/4. That is the sum of 4 times 1/2 to the k. That's 5 terms here. So I'm using 5 there. Keep in mind 0, 1, 2, 3, 4 is 5 terms. So that 5 goes there for number of terms. R is the 1/2 and 4 is your very first unit or first term. And calculation gets to that. Okay, thank you, and let me know if there are any questions. I'll be coming out with another video here soon about launching into functions as series. And that's where stuff starts to get exciting. Okay, thank you, bye.